Hello! Welcome to All A Plus Essays, the best among the best. My name is Julie and I will be your instructor as we read through ozone layer depletion and climate change. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at All A Plus Essays. The link is in the description. Greenhouse gases, global warming, ozone layer depletion and climate change have been unobserved for many years. It was not until the 1970s that the world really began to wake up to environmental issues. This was despite powers meeting before these times. The Paris Summit in 1972 led to the 1973 Communities Action Program, which set out intention to reduce pollution. The polluter pays principle was introduced as a pollution prevention measure, putting the onus on the waste producers to deal with the waste matter from their industrial processes. The first program ran from 1973 to 1976. Parliament UK&D negotiations at the Rio Summit in 1992 led to the UN Framework on Climate Change, coming into force in 1994. The objective was to stabilize greenhouse gases to a level which would avoid climate change. This was initially a non-binding agreement placed on attending countries to reduce their greenhouse gas emissions to 1990 levels by the year 2000. With no sanction against non-compliance, it became evident that a more forceful approach would be necessary in any future to negotiations with other countries. A further meeting of the powers took place in Kyoto in 1997, the UN Framework Convention on Climate Change, with the aim of reducing the effects of global warming. It took place with the aim of establishing a treaty. It was attended by most world countries. From this meeting, the Kyoto Protocol was introduced. It came into force by 2000 and historically, this was the first legally binding agreement of emission-reducing targets on the developed countries that have ratified it. J. Lambourne, Auckland, 2009. These developed countries became the A1 list, and they agreed to reduce their emissions, which were on a specific list of 6 greenhouse gases, by 5.2% below 1990 levels for the period 2008 to 2012. Other states agreed to an 8% reduction. UK&D, however, they did not stop at this. The A1 countries also agreed to establish mechanisms with the aim of cutting the costs of reducing emissions, especially with regard to poorer countries. Agreement was made to allow parties to earn and trade emission credits through projects in either of the developed countries, joint implementation, or developing countries, clean development mechanism. The trading scheme was introduced in January 2005 and put a price on businesses' carbon emissions. Member states, together, drew up a plan of allowances afforded to relevant industries, measured for example as 1 ton of carbon dioxide emission or other greenhouse gas from the list. Industries can purchase further allowances by trading with other companies with excess allowances. Negotiations to extend this scheme past 2012 are currently underway. In May 2006, the Bonn Conference was attended by delegates of 165 countries. The conference took place with the aim of strengthening cooperation. Further, the G8 conference in Tokyo, Japan saw the agreement of a vision statement, a far-reaching agreement of the future as far as 2050. Recently, scientists have met in Copenhagen in March of 2009, with the purpose of providing the most up-to-date research available with respect to the effect that climate change is having on the planet. This was in preparation of the Copenhagen, 15 Colombian pesos, due to take place in December 2009. In September 2009, at the UN Climate Change Summit in New York, over 100 world leaders stood and committed themselves to seal a successful Copenhagen climate deal. The Copenhagen, 15 Colombian pesos, will be the time when governments must reach an agreement on all essential elements on a comprehensive, fair and effective deal on climate change, ensuring long-term commitment and to launch immediate action in the fight against global warming. This is by far the biggest and most substantial movement towards tackling climate change and ensuring commitment of other countries. The UK is a small country, and although we have been one of the front leaders in the Green Revolution, it is essential that we have the cooperation of larger countries such as the US and China. The result of the 15 Colombian pesos will be the most far-reaching agreement that has ever been made in history. How does this affect the UK building services engineer at grassroots level? The EC make directives. These European directives are then fed into UK law. The results are that parliamentary acts or regulations are established which lay down the basis of building for the future. For example, every engineer must be aware of their duty of care in their building now and in the foreseeable future. The building services engineer must now be aware that the future is renewable and low-carbon resources in the prevention of pollution and conservation. Acts such as the Building Act 1984 and Building Regulations 2006 put the onus on the builder and architect, in fact everyone involved in the construction of a building, to reduce the carbon emissions as far as is possible in keeping with the regulations and further if possible. Buildings are responsible for 40% of world energy use and 30% of greenhouse gas emissions globally. UKEAND, it makes sense that these would be the most prevalent source of carbon reduction potential for the future. Our hospitals, local authorities, housing associations etc. are usually in large buildings with high energy use. These public buildings and workplaces are accessed on a daily basis. Many of these buildings have been built in pre-regulatory times when energy efficiency was not the main concern of the builders and manufacturers. There is now onus on authorities to upgrade old buildings and properties to comply with the Energy Performance of Buildings Regulation 2007. Finding alternative energy resources is now of paramount importance. The government strategy forces engineers to consider using alternatives: solar thermal hot water, heat pumps, wood fuel boiler systems, wood pellet stoves, wind turbines and cogeneration. I could go on. Some councils are now offering renewable energy grants. In April 2009, a new scheme was introduced for local authorities and landlords to provide new tenants and existing residents energy performance certificates. In the private sector, home sellers now have to provide a home information packet. This is a legally required set of documents about the property which is being sold, and as compulsory elements this includes the disclosure of an energy performance certificate, EPC, or a predicted energy assessment, P. The seller or their agent is required to have IPs in place from the first day that the property is up for sale and therefore has to obtain the services of an accredited domestic energy assessor who has the skills to survey the property to the agreed standards and provide a certificate which is then valid for 10 years. These certificates have three categories about the building's performance: the estimated operational rating, CO2 emissions and potential operational ratings. This valuable tool assists the public by making the energy efficiency of the building transparent, and the onus is on the owner to change the ratings to a more favorable number utilizing other energy resources, such as solar power, heating, combined heat and power, etc. There is further consideration of the Town and Country Planning Act 1947 in respect of planning permissions, and again the principles of conservation will be in consideration. In terms of building and manufacturing processes, the greener the company can put itself up to be, then ultimately the longer it may survive. Tackling climate change can create opportunity. It is in the interests of all involved in construction to consider that there is a real threat to their value if they fail to adopt the new innovations of greener fuels. There is rising demand for greener products. People want to trade and work with greener companies. There is reducing demand for non-green products. 1.2 Hypothesis. Although CHP has been around for many years, in fact the first electricity power station supplied local housing with the waste thermal energy produced by the generation of electricity. This arrangement came to an end with the construction of power stations in rural areas far from any suitable benefiting buildings. CHP has now in recent years had a revival, with industry and hospitals being the leaders in the large scale. Local authorities and the commercial sector have introduced CHP into district heating systems and heating of large buildings. The London Fire Service have recently completed a project to install CHP into every fire station in their area. The basis of this dissertation is to critically analyze the concept of combined heat and power within the home environment. The subject of this investigation is a 3-bedroom and terrace property in North Manchester. This is a family home consisting of 2 adults, 1 who is in full-time employment and 3 children who attend full-time education. The aim of this investigation is to examine the potential carbon savings and the benefits or disadvantages which micro-CHP can bring to this home. 1.3 Summary. The results of this analysis shall emphasize the potential that micro-combined heat and power could have on personal or carbon footprint of the home by the reduction of CO2 emissions, and also the UK government's ambitious target to cut greenhouse gas emissions by 20% by 2020 on 1990 levels, a binding target of a 20% share of renewable energies by 2020, and an agreement to implement the EU's Energy Efficiency Action Plan as the means of reducing the UK's energy consumption by 20% by 2020. 2. Literature Review 2.0 Literature Review 2.1 Introduction. Public electricity supply in the United Kingdom began in 1881. At this time, electricity was generated locally within the community it served. Although there was not a huge demand for the electricity at that time, the heat produced was used to heat local buildings with the inclusion of housing. In the middle of the 1920s, a direction of growth was developing with the establishment of large coal-fired power stations. These power stations generated electricity for bulk transmission on an interconnecting distribution network that is the national grid. Around the 1950s and 60s, large gas, oil and nuclear electricity generating plants were introduced into the network. These power plants were built some considerable distance from housing due to the pollutant byproducts or the safety issues. This meant that any heat was wasted as it could not be easily distributed to local towns or cities. In the middle 1970s, community heating was reintroduced, heating small pockets of housing within large towns or cities. In some cases, electricity was produced with the use of steam turbines. In 1995, from negotiations at the Rio Summit in 1992 led by the UN Framework on Climate Change, the government released the Home Energy Conservation Act to focus attention on the scope for increasing energy efficiency in the UK housing stock. This act put an obligatory task on local governments to assess the needs of their areas and to act as a catalyst for change. To promote the need to stabilize greenhouse gases to a level that would avoid climate change. UK DOE 1995, this act encouraged local governments to increase community heating and power schemes using small-scale combined heat and power systems. A further meeting of the powers took place in Kyoto in 1997, the UN Framework Convention on Climate Change, with the aim of reducing the effects of global warming. It took place with the aim of establishing a treaty. It was attended by most world countries, however America did not attend. Previously, President Bush had opposed mandatory emission cuts. From this meeting, the Kyoto Protocol was introduced. It came into force by 2000, and historically, this was the first legally binding agreement of emission-reducing targets on the developed countries that have ratified it. The United Kingdom agreed to reduce their emissions by 8% below 1990 levels for the period 2008 to 2012. UK L&D. This agreement produced the Building Regulations 2000 and one of the most important tools, the approved document Part L. The production of electricity has now come full circle from its beginning in 1881. Although it is not possible to generate all the electrical demand needs, combined heat and power can make a significant impact to the reduction of greenhouse gases. BREIP 4/96, generating electricity in large power stations is energy inefficient. Older oil and coal-fired stations typically have efficiencies including transmission and distribution losses of only 34%. New gas-fired combined cycle stations only achieve 44%. In comparison, small-scale and micro-combined heat and power will have efficiency in the range of 75 to 85%. DETR 2000. Combined heat and power system can possibly assist the UK government to alleviate or eradicate food poverty. 2.2 Global energy use. For almost 2 centuries, global energy consumption has grown at an average annual rate of about 2%, although growth rates vary considerably over time and among different regions. Therefore, greenhouse gases have climbed at the same rate. The principal greenhouse gas is carbon dioxide, CO2. The majority of CO2 arises from the use of fossil fuels, which in turn account for about 75% of total global energy use. Energy consumed in 1990 resulted in the release of 6 GT of CO2. About 72% of this energy was delivered to end users, accounting for 3.7 GT in CO2 emissions. The remaining 28%, 2.3 GT of CO2, was used in energy conversion and distribution. IPCC 2000A. Global carbon dioxide, CO2, Emissions from residential, commercial, and institutional buildings are projected to rise from 1.9 GT in 1990 to between 1.9 and 2.9 GT in 2010, between 1.9 and 3.3 GT in 2020, and between 1.9 and 5.3 GT in 2050. While 75% of the 1990 emissions are attributed to energy use in industrialized countries, only slightly over 50% of global buildings-related emissions are expected to be from industrialized countries by 2050. The use of different scenarios are used to predict future energy usage. The IPCC used the IS-92, which takes into account 6 different scenarios based on the principles that the global population will rise to 11.3 billion by 2100 and that economic growth averages around 2.3% per year between 1990 and 2100. Improvements in building techniques and the use of low-carbon technologies such as the orientation of the building to take advantage of local environmental conditions, increasing heat transfer properties of building materials and energy-efficient glazing, micro-CHP, PV, and solar thermal heating could possibly have a global reduction in the emission of CO2 by 20% in 2010, 30% in 2020 and 40% in 2050. This equates to 0.45 GT by 2010, 0.70 GT by 2020 and 2.5 GT of CO2 by 2050. IPCC 2000b 2.3 Energy consumption in the UK domestic environment. Although the population in the United Kingdom has rising by 4% with the number of family homes rising by 10%. Domestic energy consumption rose by 32% between 1970 and 1990. In the following 2 decades up to 2009, energy consumption has only rising by 19%. This has been a direct result of the increase in levels of insulation within the buildings and the introduction of the more electrical efficient appliances. DTIA 2001, Revision 3. Regardless of the increase in the quality of insulation materials, the majority of the energy used within the home is due to space heating. Space heating accounts for 61% of the total energy used within the home. The other areas of use are 23% for water heating, 13% for lighting and appliances, and 3% for cooking. In 1970, 5.6 million or 33% of the UK housing stocks had central heating compared to 22 million or 89% in 2006. In the 30 years from 1970, the energy consumption for lighting and appliances increased by 157%. This was due to the increase and availability of lighting and a move from having a single luminaire to light a room to having multiple table lamps and electrical appliances such as washing machines, tumble dryers and dishwashers, home PCs, DVDs, etc. The proportion of one-person households has almost doubled from 17% in 1971 to 32% in 2000. Part of this increase has been driven by the rise in life expectancy since the early 1970s, 50% of those aged 75 and over live alone, compared with just 12% of 25 to 44-year-olds. The amount of energy required by 2 people living in 2 households is greater than the amount of energy required by 2 people living in the same household, therefore increasing the number of fuel poor. 2.4 Fuel poverty. A household in fuel poverty is now widely defined as one that needs to spend more than 10% of its income on all household fuel use, including heating its home to an adequately warmth recommended as 21 degrees Celsius in the living room lounge and 18 degrees Celsius in other occupied rooms, World Health Organization. The average household spends approximately 5% of their income on fuel. With the essential investment that is required for the prevention of climate change, energy costs are predicted to escalate, and in addition to the present economic climate of growing unemployment, fuel poverty or the number of fuel poor is expected to rise. 4.5 million people are affected, with 2/3 being in the private sector. Daily Mail. This is a nationwide problem, with 6.8% of the population oppressed and fuel poor in the affluent areas such as Kensington and Chelsea, with a fuel poor population of 5.1%, DTIB, 2001. Fuel poverty affects the most vulnerable in society, such as older people, especially those living alone. Households with children, including lone parenting. Households with sizable adult inhabitants, disabled physically and mentally, and single-person occupancy. As fuel poverty has an impact on health services, it is often the health service that deals with the effects of cold, damp housing and inadequate heating on their local communities. Fuel poverty is a major health concern, both in terms of its effects on health and the additional pressures it places on local health services, especially during the winter months. Fuel poverty and health. Since 1990, the number of households has increased by 10% and the population has increased by 4%. The UK government has a target to abolish fuel poverty by 2017. Micro-combined heat and power systems are perceived as being able to abolish this. That if fuel poverty is to be eliminated, extensive solid-wall insulation is not necessarily required because micro-CHP can do almost as much as solid-wall insulation to reduce bills, climate change and fuel poverty. With 2/3 of those caught in fuel poverty belonging to the private sector, there must be special provisions made, such as low-income grants or loans to encourage this group to invest in low-carbon technology while elimination fuel poverty. J. Watson et al. Energy Policy. 2.5 Combined heat and power, small scale. Combine heat and power using a number of different types of fuel and either internal, external or fuel cell technologies have been successfully serving to reduce greenhouse gas emissions while reducing the demand on the grid network. Alternatively, the micro-combined heat and power designed to heat and supply all or subsidize the production of electricity from the grid is a relatively new technology. Micro-combined heat and power, micro-CHP, installed within the domestic housing market can help to meet a number of energy strategy and social objectives. These are reducing greenhouse gas emissions, predominantly CO2 from centralized power generation, improving the security of energy supplies by the increase of decentralized generation and removing the waste of transmission losses on the distribution grid. Another benefit can be a saving to the consumer's energy costs and possibly assisting to eliminate fuel poverty. DTIC. Micro-CHP systems along with other type of micro-generating, that is photovoltaic, solar, thermal etc. may well contribute to as much as 40% of the electrical demand and 15% of the household CO2 in the UK by 2050. Energy Saving Trust 2005b. A number of CHP operating strategies due to either driving by an engine or a fuel cell have been studied. These are typically simple strategies such as heat-led, where the electrical generation begins when a heat load is present, or electricity-led, where the heat generation begins when an on-site electricity load is present. Peacock AD et al. The first has investigated 4 of the distinct prime mover operating modes for micro-CHP in the UK. He investigated variation in the length of operating time per day, size of the prime mover, and whether or not to charge an electricity storage bank. No attempt was made to minimize the cost of operation, as this was thought to be difficult in practice, and no consideration of thermal management was undertaken. Thermal load was assumed to be that of micro-CHP thermal output per day. Peacock AD et al. Conducted a study into micro-CHP control logic where the prime mover is activated, deactivated or turned down. Specifically time-led, heat-led or electricity-led, on-off according to user-defined program, but dispatched under the presence of a heat load. Control was applied, in combination with a number of thermal constraint arrangements. The industry point of view was similar in that micro-CHP is usually assumed to be heat-led. COG in Europe state that micro-CHP is a replacement for conventional gas boilers in domestic dwellings, with the micro-CHP unit operating in a heat-led mode. Harrison J. et al. Suggests that electricity is a byproduct of micro-CHP unit heat production. This heat-led assumption appears to be true for the first technology to mass market in the UK. The Stirling engine typically operates in a heat-led mode, dispatching the engine against heat demand, and a supplementary heating unit, either an integrated condensing boiler or other integrated heating unit, where the engine's output is insufficient to meet this demand. However, other micro-CHP technologies have the ability to modulate output, and future generations of current technologies may incorporate this feature if the economic case is strong. Alternatively, Hawks et al. Investigates more complex and off, where the cost of operation and or other parameters such as emissions are minimized, dependent on fuel used. Where micro-CHP control strategy is optimized to ensure the ability to meet simultaneous loads as an alternative to grid electricity or backup thermal systems using. Present a comparison of operating strategies from an economic viewpoint for micro-CHP, a fuzzy logic ideal for off-grid use. INTKIV E. Although the primary aim of this article is the subsidiary theme of the investigation is to determine if it makes economic, environmental, and technical sense to operate in a heat-led manner. Micro-CHP systems are heat-constrained in that it is difficult and potentially environmentally damaging, and within the UK, contrary to approved document Part L of the Building Regulations 2006, to dump excess heat from the system, except to a recognised facility, such as swimming pool or buffer vessel, etc. This procedure would eliminate the majority of the housing stock. However, it is not necessary to operate in a heat-led dispatch mode simply because the system is heat-constrained. The presence of hot water cylinder in the system decouples heat production from demand, and as with conventional boilers, there are options to dump small amounts of heat from the system, for example via a fan-assisted flue. The heat-constrained nature of system dispatch is further relaxed for technologies with low heat-to-power ratios such as fuel cells, because less heat is produced for a given electrical output. More cost-effective dispatch modes may improve the economic case for the technologies, and decrease overall greenhouse gas emissions from meeting energy demand. 2.6 System Types. 2.6.1 Internal combustion engine. The internal combustion engines for micro-CHP units are similar to that found in a car but designed most commonly to run on natural gas or LPG, but can be designed to use biodiesel, fuel oil, etc. Like a car engine, because of its complexity, it requires servicing at set service intervals depending on size. This type of engine is predominantly used with micro-CHP with a higher thermal output and a larger area in which to store the plant. A micro-CHP, which is small in size, around the size of a floor-standing combination boiler, has been developed using a 4-stroke internal combustion engine for the Northeast American market. This type only produces an electrical output of 1 kW and thermal output of 3.3 kWt. It has to be designed to be linked with a boiler to produce the required comfort temperature for the home. The internal combustion engines are relatively low in noise but are required to be installed in plant rooms or outside, as the level of noise is unsuitable for installation in occupied areas. This type of engine is heat-led and produces a power ratio of between 0.3 and 0.5 with efficiencies up to a maximum of 98%. Having plant rooms within the home or outside is suitable for large property types in North America. The micro-CHP market in Japan is similar, with most Japanese homes having their heating appliances usually stored outside of the home. In Japan, there has been a significant amount of units sold, 45,000 within a 3-year period from 2004 to 2007. Within the UK, there has been a significant take-up of internal combustion micro-CHP, with the London Fire Service installing one in the majority of their stations, also used in small residential communities such as retirement housing, etc. 2.6.2 Stirling engines. Stirling engines are external combustion engines, which allow continuous, controlled combustion resulting in very low pollutant emissions and high combustion efficiency. They can operate without valves or an ignition system, thus permitting long service intervals and low running costs. All Stirling engines fall into one of the following 2 basic categories. Kinematic Stirling engine: a Shava crank arrangement to convert the reciprocal piston motion to rotational output, say to drive a generator. The displacer is actuated through some form of mechanical linkage. A9AYTZ2XYY. This style of Stirling engine are sadly considerably larger, the free piston type, and are suited to the market similar to Japan, where boilers and MCHP are installed outside the property. Free piston Stirling engines, FPSE, have no rotating parts. In the majority of cases, output power is taken from a linear, usually permanent magnet, alternator attached to the piston, while the displacer is actuated by the pressure variation in the space beneath the piston. Stirling engines can also be characterized by the 3 typical configurations of the displacer and working pistons, known as alpha, beta and gamma. 2.6.2.1 Alpha type engine. In the alpha type, the working gas shuttles between 2 pistons. One piston carries out compression in the cold space and the other, expansion in the hot space. A subdivision of the alpha type is the double-acting type, where useful work is done by symmetrical pistons. This type has been manufactured in New Zealand, where the engine works with 4 cylinders acting on a double configuration using nitrogen as the working gas. In turn, the pistons are attached to a wobble yoke mechanism which rotates an armature. 2.6.2.2 Beta type engine. In the beta type, both compression and expansion are carried out by the working piston, the working gas being shuttled between hot and cold spaces in the same cylinder by means of a non-working displacer. 2.6.2.3 Gamma type. The third version is the gamma type in which the working piston is placed in a separate cylinder. 2.6.2.4 Engine type summary. It has been shown that the beta type is inherently more efficient than others. High efficiency alone is not necessarily a desirable goal. Indeed, measures which improve efficiency may have undesirable consequences both in technical and economic terms. Clearly, there is little point in achieving a high efficiency if the production costs are so high that it could never be recovered from energy savings. INCAV. For example, it is possible to improve the Carnot efficiency of a Stirling engine by using discontinuous motion of the piston. Practical implementation of this feature is possible using electromagnetic actuation of the displacer, and is to some extent simulated in the conventional crank arrangement of some engines. However, fluctuations in rotation of the working piston give rise to other complications, particularly variations in electrical output and high electrical losses, as well as obvious increases in noise, vibration and mechanical stress. Thus, the quest for high efficiency has economic and performance implications which may be undesirable. Indeed, the engine manufactured in New Zealand has an inherently low electrical efficiency, but with reliability and production cost parameters in line with market requirements can be seen as a major landmark in the commercialization of micro-CHP. 2.6.3 Fuel cells. The technology of fuel cells is not yet fully developed and few products are commercially available at the moment. The products which are available are aimed at large industry. Although a British manufacturer has been contracted by major energy suppliers throughout Europe to supply fuel cell micro-CHP. These units will be commercially available by the second half of 2011. Fuel cells are generally classed by the electrolyte used. There are four main types used in CHP: phosphoric acid fuel cell, PAFC, proton exchange fuel cell, PEMFC, molten carbonate fuel cells, MCFC, and solid oxide fuel cell, SOFC. The most suitable fuel cells for microgeneration is the solid oxide and proton exchange fuel cells, which have an electrical efficiency of 45 to 50%, and with the SOFC's high operating temperature of between 800 degrees Celsius and 1000 degrees Celsius leads to high efficiency in heat transfer. Fuel cells convert the chemical energy of hydrogen and oxygen directly into electricity, without combustion and mechanical work such as in turbines or engines. The hydrogen is usually produced from natural gas by a process known as reforming. The total efficiencies of cogeneration systems reach 85 to 95%. Fuel cells micro-CHP systems typically will have a capacity of 1 to 2 kW and characteristically have the highest power-to-heat ratios, expected to be in the range of 0.7 to 2.4. They can therefore potentially be run in an electrically led operating mode, sized to generate electricity constantly with the associated heat, providing a small part of the overall on-site heating or hot water requirements, with a separate gas-fed heat exchanger providing the remaining heat needs. When used in micro-CHP applications, fuel cells have the potential to save energy and reduce emissions depending on the fuel cell technology used, and their inherent fuel flexibility could help address energy shortage issues through energy diversity. In addition, fuel cells have the potential to be quieter, more reliable, and have lower maintenance costs than some of other types of technologies used for micro-CHP. 2.6.4 Power-to-heat ratio. The power-to-heat ratio is a significant guide to discovering the prospective savings on CO2. The greater the power-to-heat ratio, equates to better generation of electricity. The micro-CHP systems are required to be designed to meet the residents' heat demands and are used effectively. Due to the diverse needs of residents, systems must be designed to obtain the optimum heat-to-power ratio. Stirling engine micro-CHP systems typically have power-to-heat ratios in the range of 0.1 to 0.25, 110 to 1:4. As a consequence, they are well suited to operating in a heat-led fashion in domestic environments, sized to meet the full heat demand. In the absence of attractive export reward tariffs, they are also normally sized to generate electricity at a level that ensures that a reasonable proportion is used within the household rather than exported. INTKIV E. 3. Methodology 3.0 Methodology 3.1 Methodology available. Micro-combined heat and power systems are designed to be direct replacements or new installs for conventional floor or wall-mounted domestic gas boilers. To determine if micro-CHP is suitable as discussed in the hypothesis, the required heat load needs to be discovered along with the period the heat is necessary. There are several methods of how this can be attained. The use of simulation software such as Havicom can produce a theoretical conclusion. The assessors carrying out the energy performance of buildings use the RDSAP 2005 assessment methodology, which is software-based. Building dynamics are extremely complex and thermal capacity specifically has by no means been adequately dealt with in simplified energy estimation models. Another way of discovering the required information is the degree-day methodology. 3.2 Selected method. The method chosen to achieve the hypothesis is the heating energy estimation procedure set out in CIBSE Degree Days Technical Memorandum 41. This practice allows for the setting up of a Microsoft Excel spreadsheet to aid in the estimation of the energy consumption along with the carbon dioxide emissions due to the space heating of the building. Heating degree days are a measure of the severity and duration of cold weather. The colder the weather is in a given month, the larger the degree day value for that month. They are, in essence, a summation of the difference between a reference or base temperature and the outside temperature. When the outside temperature rises above the base temperature, degree days are taken as 0. This summation for each calendar month is published as historical data by CIBSE. CIBSE got A. The rate of heat loss from a building is directly related to the inside to outside temperature difference, and the energy consumed for space heating is directly related to degree days. This relationship between energy consumption and degree days can be exploited to appraise the energy performance of a building, to detect energy waste, system faults, and to set realistic budgets. The base temperature is defined as the outside temperature above which the heating system in a building need not operate. The heat in a building comes from several sources, as well as from the heating system itself. These other sources include the occupants, lights, and equipment in the building. This means that a building is partially self-heating and the base temperature is therefore lower than the internal temperature. 3.3 Summary. The theoretical analysis chosen will provide detailed and accurate examination of the energy consumption and carbon dioxide emissions from an average 3-bedroom house situated in Manchester in the northwest of England. This will allow for the suitability for micro-CHP to be determined as to whether cogeneration can reduce carbon dioxide while producing space heating and electricity to be used within the home or exported. 4. Investigation. 4.0 Investigation. 4.1 Introduction. This investigation will research into the viability of installing a micro-combined heat and power system within a domestic dwelling. The subject of this investigation is a 2-story 3-bedroom property in the North Manchester area. It comprises on the ground of a lounge, kitchen, WC and storage space. The second floor consists of 3 bedrooms and a bathroom. This type of property makes up 70% of the total low-rise local government housing stock and as such should produce a median standard. The building is constructed in 1968 using a cavity brick-style construction with rough cast rendering to the exterior, on a screed and cast concrete floor. The roof construction is made of plasterboard mineral wool insulation and tiled exterior. The property was at improvement done under a recent Decent Homes program. This comprised of upgrading the glazing from single to double glazing, installation of cavity wall insulation and increasing the existing 100 mm loft insulation with a 150 mm mineral wool quilt above the joists. This building is an end terrace house situated in the Newton Heath area of the city and has the address of 9 Lannisfield Walk. 4.2 Energy Performance of Buildings Regulations 2007. UK had to devise a scheme from a directive from the ECC. The Energy Performance Certificate Scheme is part of a series of measures being introduced across Europe to reflect legislation which will help cut buildings' carbon emissions and tackle climate change. Other changes include requiring public buildings, for example town halls, libraries, hospitals, to display certificates showing the energy efficiency of the building and requiring inspections for air conditioning systems. If you are buying, selling or reletting a home, you now need a certificate by law. From October 2008, EPCs are required whenever a building is built, sold or rented out. The certificate provides A to G ratings for the building, with A being the most energy efficient and G being the least, with the average up to now being E rating 46 feet. Energy performance certificates are required to be produced by a qualified assessor using the RDSAP 2005 assessment methodology under the statutory legalization of the Energy Performance of Buildings Regulations 2007. The energy assessors also produce EPCs alongside an associated report which suggests improvements to make a building more energy efficient. The general relationship between various CEN standards and the Energy Performance of Buildings Directive, EPBD, are covered under the umbrella document CEN-TR 15615, of which included the following technical committee reports and EN guides. CEN-TC 89 Thermal Performance of Buildings and Building Components. CEN-TC 156 Ventilation for Buildings. CEN-TC 169 Light and Lighting. CEN-TC 228 Heating Systems in Buildings. CEN-TC 247 Building Automation, Controls and Building Management, EN 15217 Assessment of Energy Certification, EN 15603 Overall Energy Use, EN ISO 13790 Thermal Performance of Buildings. Although this list is not exhaustive, the above list covers the main aspects of the Energy Performance of Buildings Directive. An energy performance survey has been carried out on this property on the 22nd February 2010, which produced the following: the estimated energy use of the house. The figures in the table above are provided to enable future tenants to compare fuel costs and carbon emissions from one home to another. To enable this comparison, the figures have been calculated using standard running environment, heating periods, room temperature, etc. that are the same for all homes. As a result, they are unlikely to match an occupier's actual fuel bills and carbon emissions in practice. The table below gives an assessment of the fundamental distinctive elements that have an influence on this home's energy and environmental performance. Each element is assessed by the national calculation methodology against the scale of very poor, poor, average, good, very good. The Energy Performance Certificate does not take into account the location or orientation of the building, and as the RDSAP 2005 assessment methodology is a software program, it is prone to the inputting of imprecise information. Therefore, the analysis of the evaluations may be ambiguous. To estimate more precisely the energy consumption and carbon dioxide emissions due to the space and hot water heating, a method such as the degree day approach shall be used. 4.3 Fabric heat loss. Where a temperature difference occurs between the inside and outside of a property, heat will flow through the structure towards the lower of the temperatures. This heat flow, loss, will occur through walls, floors, roofs, and windows, and even between rooms of dissimilar temperatures. It is important to know how much heat is lost through each structure so that calculations can be made to heat a building to the desired temperature. The transfer of heat is calculated using U values together with the surface areas of the various structural components and the temperature difference between the two sides of the structure concerned. For ease of calculation, it is assumed that heat is lost at a uniform rate through each surface. The U value of a building element is the rate of loss of heat in watts per square meter of that element per degree centigrade temperature difference across that element. Thus, the rate of loss of heat through a building element is given by 4.4 Ventilation heat load. The assumed type of ventilation is in the interest of energy efficiency and shall be natural ventilation. The requirements for the provision of ventilation in dwellings are detailed in the building regulations are to restrict the buildup of moisture and pollutants, which would otherwise be a hazard to health. This ventilation air, flowing through the building, loses heat. Ventilation rates are usually quoted as air changes per hour, defined as the volume of ventilation air moving through the building per hour, divided by the volume of the building itself. The air will be heated by the heating system, and the heat needed is calculated by multiplying the room volume, by the air change rate, by the temperature rise the air needs, and by the ventilation factor. Thus, the rate of loss of heat through ventilation loss is given by ACH temperature. The ventilation factor is taken as the specific heat of air at 20 degrees Celsius, which is 0.33 W/m3 degrees Celsius, and is used to calculate the heat loss to the air changing within the building due to natural ventilation. 4.5 Infiltration heat load. Infiltration heat load is due to outside air entering the building and warm air escaping due to factors such as external wind pressures through gaps in windows, doors, etc., and difference of the internal and external temperatures. Infiltration can also be referred to as air leakage. Infiltration is dependent on the air tightness of the building. Taking from CIBS ETM 23, the good practice air leakage for a natural ventilated dwelling is 8.15 pascals per meter cubed H to the first m squared at 50 Pa. The following formula is used to determine the infiltration rate in ACH. In this dwelling, the infiltration ACH 0.425 equals 235 times 0.425 times 26 times 0.33 equals 875 W. 4.6 total heat load for the building. The total heat load is calculated by the accumulation of all heat losses. 7127 plus 1008 plus 857 equals 8992 W. 4.7 building heat loss coefficient, U, kilowatt per carat. The heat loss coefficient is an evaluation of the tempo of heat loss through the building materials. 4.8 building thermal capacity. The building thermal capacity is the quantity of heat necessary to produce a unit change of temperature in a unit mass of a substance. Thus, building thermal capacity is given by C equals 10,530,250 J. 4.9 thermal output of the plant QP, kilowatt. The thermal output of the plant is taken from the total combined fabric heat loss, ventilation heat load, and the infiltration heat load. Also taken into account is the daily supply of hot water. The daily amount of hot water is estimated using the BSRA rule of thumb to be 165 liters per day. To heat this water to 65 degrees Celsius from an average cold water intake of 12 degrees Celsius requires 36,729 kilojoules, equating to 10.2 kilowatts. This sum is divided over 24 hours equals 425 W. The plant output will be the design heat loss with some added margin. In this case, a ratio of 1.2 has been used. CIBSAC, total heat load equals 7127 plus 1008 plus 857 plus 425 equals 9417 times 1.2 equals 11.3 kilowatts. 4.10 plant average efficiency. The building is heated using Super Mexico FF boiler fitted in 2002 with a seasonal efficiency rate of 79.9% and efficiency band D. 4.11 average casual gains to the space. Casual gains from occupancies assume that a family of 5 live within this dwelling with 1 adult working and 3 children at school during day. Assuming each person emits 80 W of sensible heat. Average occupancy gain equals 183 W. Internal heat gains from heating and lighting are minimal, so we'll add a nominal sum of 200 W. Average casual gains equals 183 plus 200 equals 383 W. Please be aware that the free essay that you were just reading was not written by us. This essay, and all of the others available to view on the website, were provided to us by students in exchange for services that we offer. This relationship helps our students to get an even better deal while also contributing to the biggest free essay resource in the UK. Thank you for taking your time to listen to me. I hope you enjoyed learning about ozone layer depletion and climate change as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at All A+ Essays for as little as $10. The link is in the description. See you next time.